Okay, so here's the bleaching example from week 2 homework. Again, what's plotted on the x-axis is the sea surface temperature anomaly in degrees centigrade from the average temperature over some period of time that I've forgotten. And what's plotted on the y-axis is the percentage of cells bleached, where coral bleaching was reported. This has been back transformed onto the original axis. The data and the graph in the paper are, of course, on a log. The y-axis is on a log scale. So when you put it back into the linear scale, the function is now no longer even remotely linear. It's an exponential increase. And here's the maximum observed data point in that data set up to this point in time. But as with in the Guthrie and Bingham paper, what was done was to sort of project upwards and ask at what point are we going to see 100% bleaching? So to do that, we draw a horizontal line here. In the paper, they focus on the average, but of course, the lower or the upper prediction limit, given by the dotted line, crosses the boundary at a much lower SST anomaly. If we're interested in evaluating the quality of this model, we can look at the QQ plot, as we've done, and other residual plots, and we see that it doesn't look too bad. These 4 points at the top are these so-called mass bleaching events, where we see large proportions of the cells are actually bleached. So it doesn't look too bad, and you might not think it's a terrible fit. Indeed, the reviewers at Ecology didn't think it was a terrible fit. But 100% is a maximum, and so as we could see from the figure, a linear model is perfectly happy to project observations above 100% cells bleached. So let's think about the structure of the data a little bit. What we've got are 92 cells. Each of them is bleached or not bleached. So let's look at coin flip, heads or tails. And we're going to get a number somewhere between 0 cells bleached and 92 cells bleached. We can't have any other number. This kind of distribution is a binomial distribution with n, the number of trials, and p as the probability of getting a head. So what we're trying to model is p. What is the proportion of cells that are bleached in any one year? N is fixed at 92. Now it turns out the normal distribution is a pretty good approximation of a binomial distribution when n, that is the number of cells, is large and p is not close to 0 or 1. So there's two problems with this. It's when temperatures are low or around average, we get very few bleaching events. That is, the proportion of success is close to 0. So again, the normal is not going to be a good approximation there. And when we want to extrapolate to find where 100% of the cells are going to be bleaching, well, that's also where the normal approximation is going to break down. This formula down here shows us the probability of getting X, say 32 cells bleached, given some probability of success and some number of trials. We won't need to go into that in any great detail. So how do we fix this problem? Well, what we're going to do is we're going to shift our gears a little bit, and we're going to use generalized linear modeling. We're still going to have a linear relationship between our predictor variables and something. That something will become clear in a moment. That's called the linear predictor part of these models. So just as before, we're going to have an intercept and some coefficient for the covariate x. We're going to call the linear predictor with this Greek letter nu. Then what we do is we add a link function. What the link function does is convert the expected value of the response onto this linear predictor scale. So this linear predictor can go between minus infinity and plus infinity, just like a regular linear model can. But our response, for example in the bleaching case, is limited to be between 0 and 1. It can't go up to minus infinity, or between minus infinity and plus infinity. So as a result, we need some kind of function that's going to convert the scale from 0 to 1 onto minus infinity to plus infinity. And the default link for a binomial model looks like this. It's called the log odds or logit link. We take the expected value of the y's, that's our number of, in this case the number of cells bleached, divided by the number of cells that don't bleach, n being the total, the expected value of y being the ones that we want, and then so that's the ratio of the successes to the failures, and then we take the logarithm of that. That quantity is going to be equal to our linear predictor. Then the second thing we need to move from generalized linear modeling, or from linear models to generalized linear models, is we now have to allow for our observations to have a distribution other than normal. And so in this case, our distributions are going to be our observations, are binomial. So we're going to get p and n together give us the expected value of the y, but this distribution gives us the probability of getting any particular value of y, not the expected value. And so given p and n from this equation, we can calculate the probability of an observation of, say, 35 cells bleached, and as a result, we can calculate the likelihood and then also get the fit our model. Let's take a closer look at the linear predictor. Linear means there's only pluses and minuses between terms. So our intercept and our covariates are connected by plus or minus. There's no multiplication, no exponentiation, nothing like that. This covariate here, just like in our other linear models, can be a continuous variable or it can be a factor, a categorical variable like sex or species. And just as in linear models with multiple regression, we can have more than one term. So we have multiple predictor variables operating in here. Link functions are where it really gets a little tricky to understand mentally what's going on. What a link function does is it converts the expected value of the response to the scale of the linear predictor. So the expected value of y is what does the sample mean as the sample size goes to infinity. It's tempting to think of these as a transformation, but it's not a transformation of the data. When you transform your data, you're taking the individual observations of your response y and then doing something to them, taking the logarithm in the case of the bleaching example. The link function doesn't apply to the individual observations, it applies to the expected value of our observations. For a normal linear model, we can think of it as having a link function, and that link function is the identity function. It doesn't do anything. The expected value of the y is exactly equal to the linear predictor. For binomial or presence-absence data, so presence-absence being 0 and 1, where you only have a single trial, we use the logistic link, which I already described. So that's the logarithm of the odds ratio. For count data, where we don't have an upper limit to the number of observations, we can just take the logarithm of the expected value. That's called a log link. And those are the two most common cases that we're going to deal with here. So the expected value of a Poisson distribution, take the logarithm of that. That thing is going to be linear. Error structure. So now, given that expected value of y, what is the distribution of our observations? And this sometimes can come with an extra parameter that measures something like the variance. So in a normal error distribution model, normal linear model, we have the expected value of y, and we also estimate a dispersion, or the variance of our residuals. For proportions, we're going to assume that we have a binomial distribution. So now our observations are discrete. They're between 0 and some upper limit n, and our probability of p of getting a success is just the expected number of heads divided by the number of trials. And for counts, we use a Poisson distribution. Again, it's discrete. 0 is the lowest number you can get, then 1, 2, and so on, but there's no upper limit. Any number is in fact possible. If we go back to the bleaching example and refit our observations as if they're binomial observations now, which they are in fact, and then extrapolate with our model, we now get quite a different expectation. Now the red line shows us what happens when we extrapolate, and we're going to end up with, and these again are prediction intervals, so now we're going to end up with coral reefs being much more robust to temperature anomalies, or rather, well, perhaps not more robust, but it's going to take much higher temperature anomalies to cause a complete catastrophe. 50% of the cells bleaching is bad enough. So because we are actually recognizing that we can't have more than 100% of the cells bleached, we're going to end up with a very different relationship between the percentage of cells bleached and our predictor variable down here on the bottom.